Welcome to the second image segmentation lecture. This week, we have 3 topics. First, we will talk about evaluating performance of automated segmentation. We will discuss overlap measures and surface distance measures. Then we will see how we can use registration to achieve image segmentation as well. And finally, we will have a high-level overview of deep learning segmentation. So let's start with the first part, evaluating performance of the segmentation. So the first question we need to ask, how do we go about it? How do we evaluate the segmentation? And usually what we do, we compare the automated segmentation to a true segmentation. So let's have a look at the example here. What we want to do, we want to segment cortex in fetal MRI. And this is the ground truth segmentation. That's what it should look like. And for that, we use 3-class Gaussian mixture model. And this is the automated segmentation that we get. You can see that the segmentation is not extremely good because we didn't only get the cortex, we mostly got the cortex, but we also got other structures like these deep gray matter structures and some spurious voxels in the background. The reason for it is that the Gaussian mixture model works only based on intensity, and there are other structures in the image that have similar intensities to the cortex. So that's why the segmentation doesn't work so well. But let's now focus on how we compare these two segmentations. And here you can see the colored overlay of these two segmentations. Here is the legend. So yellow voxels are the ones that are correctly segmented. So they are both in ground truth and in the automated segmentation. And these are called true positives. In purple, we have voxels that we have missed. So for example, here I can see some purple voxels in this area, and you see that it's kind of solid here, the cortical ribbon, and here we have a break. So we see that some voxels haven't been segmented that are in the automated segmentation. And finally, green, or maybe we can call it khaki, this kind of color are the extra voxels that are not in ground truth segmentation, but were segmented using Gaussian mixture model. We call them false positives. The missed voxels are called false negatives. So the next question we need to answer is where we get the true segmentation from. And true segmentation is also called the ground truth. And ground truth is also referred to as gold standard, but unfortunately for real patient data, the ground truth is not known because we don't know the true shape of the organ or tissue properties, so we can't really be sure what is the true segmentation. We only can have ground truth segmentation for simulated data, and you can see an example of brain web. Brain phantom here. So this phantom has a shape and tissue properties of a real human brain. And this is then put into MRI simulator to simulate an MRI image, which is a fake image, but it's kind of realistically looking. And then we can use this kind of simulated MRI to test our techniques and have the ground truth segmentation available. However, we are often primarily interested in evaluating our segmentation techniques on a real patient data, and we don't really have ground truth. So instead, we have to use some kind of estimate of a ground truth. And to do that, we usually use expert manual segmentation. So the expert rater will be manually drawing in some kind of software package such as ITK Snap. And ideally, that's an experienced clinician, but very often it can be trained PhD student, postdoc, or clinical fellow as well that does these manual segmentations. Of course, this can be a very time-consuming process. Nobody likes to do that, but it's usually the only option that we have. So problem with manual segmentation, though, is that they are prone to errors. And here you can see an example of manual segmentation of a lung lesion in CT. And if you look in detail at the boundaries, you can see that each of these segmentation have slightly different boundary. And this is all the same image. So you can see that it's not completely clear what the correct segmentation is, and there are errors. Fortunately, we can at least measure these errors if we have multiple manual segmentation. So we can measure intra-observer variability. That's when the same expert segments the image multiple times, or inter-observer variability when different experts segment the same image. So in practice, though, the manual segmentations are often referred to as ground truth, even though they are not strictly speaking a ground truth. And we will refer to them as ground truths as well from now on. So now that we know where our ground truth comes from, let's look at the measures we can use to evaluate our segmentation. So most common measures are called overlap measures, and they measure how much automated segmentation overlaps with ground truth. So what do we mean by overlap? So if the segmentation have no intersection, they are completely distinct, then we say that they have no overlap. If they have partial intersection, but they are not completely identical, then they have partial overlap. And complete overlap means that the segmentations are identical. The most common overlap measure is Dice coefficient, and this measures the overlap between automated and ground truth segmentation. So let's say that A here represents the automated segmentation, the red ellipse, and B represents the ground truth. Then the overlap will be A intersection B, so this area here. And so this is our intersection or overlap, and we need to get the area of the overlap or a volume of the overlap, and we do that by counting the number of voxels in the overlap. So it will be number of voxel in the intersection times 2 divided by a number of voxels in the automated segmentation plus number of voxels in ground truth. If you take this number 2 down here into the denominator, you will see that it's actually overlap over average size of the segmentation, because ground truth and automated segmentation might not have the same number of voxels, so we take the average to calculate the size. Okay, so let's have a look at a simple example of Dice coefficient. So here we have identical segmentation, so Dice coefficient will be 1. And then you can see examples that the overlap is getting smaller and smaller, and Dice coefficient is decreasing as the overlap is decreasing. And finally, when there is no overlap, we will have Dice coefficient of 0. There is one caveat though. Dice coefficient is not an absolute measure, and it will depend on size and shape of the structures. So to demonstrate that, we have here some kind of an artificial example. So this is a ground truth segmentation for different brain structures in fetal MRI. So here we have the whole brain, including CSF, sometimes called intracranial volume as well. Here we have deep gray matter, white matter, cortex, and ventricles, and it's all done only in one slice here so that you can see the whole structure. And what I've done in this artificial example, I shifted the ground truth segmentation by 1 voxel in both X and Y direction. So we could say I shifted it by 1 voxel in diagonal. And then I calculated Dice overlap between the original segmentation and shifted segmentation. And you see that when we have this kind of large structure, relatively round, the Dice hasn't dropped so much. We have 0.97, which is still very high. For nice round but smaller structure, Dice drop a little bit more. It's 0.91. That's because we have more voxels on the boundary than in this case. So there will be more errors compared to the inside of the object that is still correctly segmented. Now, this is still a relatively large structure-wide method, but it has quite more complexity with some thin structures as well. So this results in an even larger drop of dice. Cortex is very thin, so drop will be even larger. So 0.71 dice here. And a small structure again has almost all the voxels on the boundary. So again, we have a drop. So here you can see how dice coefficient will depend on what exactly your structure that you try to segment looks like. And finally, I want to show you the dice coefficient for our example of segmentation of cortex in fetal MRI using Gaussian mixture model is 0.68, which is not a very high dice coefficient. So this tells us that this segmentation is probably not very good. Dice coefficient is not only overlap measure that we use. Another quite common one is called Jacquard coefficient, and this is calculated as intersection of a union of the segmentation. Jacquard coefficient is directly related to dice coefficient using this equation, so it actually doesn't give us any new information compared to dice. Okay, let's move on to surface distance measures now. These give us complementary information compared to overlap measures because they measure the distance between surfaces of automated and ground truth segmentations. So if we are in 3D, we talk about surfaces. If we are in 2D, as we are in this here in this diagram, then we can talk about contours. So what does it mean? So if I take a point on this red contour, let's say, I want to measure the distance to the blue contour, then I have to work out which pixel is the closest. So it's this one, let's say, and then I measure the distance between this pixel and this pixel. And I do that for all the points on this contour. And then I need to do some summary measure of that. So Hausdorff distance takes the maximum distance from a point on one surface to the nearest point on the other surface, which means that we find the minimum distance for all the points and then get the maximum. So that's expressed here in this equation. So A is a point on the red curve, let's say. Then we find the closest point on the other curve, which will be the B. So that's expressed here by the minimum distance. And then we take maximum over all points A. Okay. Also, if you do it from red curve to blue curve, you will get different number than from blue curve to red curve. So that's why we take a maximum of these two values to get the final Hausdorff distance. We might also be interested to take average instead of maximum, and then we talk about average surface distance. So again, the algorithm is the same. Here we first find for each point on the first curve A, we'll find the point on B that is the closest, and then we take the distance of these 2 points. But instead of taking maximum, we will take the average. And again, it's not symmetric, so we will take the average in both directions. Just a little note, we will use simple ITK to calculate these measures in the tutorial, and simple ITK call average surface distance, actually average Hausdorff distance. And here is our example that we already used for dice. So here you can see what is the Hausdorff distance and average surface distance. So Hausdorff distance, interestingly, is the same for all the different structures, and it's 1.41. And this makes sense because we did translation in the direction of diagonal of a voxel by just one voxel, and the diagonal of the voxel will be exactly 1.41 of the voxel. So it makes sense that you cannot have higher distance than that. So in this case, Hausdorff distance was exactly the same, independent of size and shape of the structure. However, average surface distance does vary. That's because it really depends on the orientation of the curve. So if the curve is oriented perpendicular to the direction of the shift, there will be a big error. If it's parallel, then we will not see any error. So that's why we see different numbers depending on the complexity of the surface. So let's have a bit closer look. How do we calculate these surface distance measures? And we'll again come back to the segmentation of fetal cortex. So the first thing that we need to do is to calculate this distance transform for both segmentations. So this distance transform gives us a value for each voxel, and this value will be the shortest distance to the surface of the segmentation. So here you can see that if we take all the voxels with 0, we will get exactly the surface of the segmentation. So 0 contour of this distance transform will be the surface of our segmentation. This distance transform can be calculated with an algorithm that is very similar to region growing. While we grow the region, we also track the shortest distance to the surface, and it can be done quite efficiently that way. Now, once we have this transform, we will switch the contours. So here we have the distance transform of the ground truth, and the contour is from the automated segmentation, and here it is the other way. And then what we will do, we will collect all the distances on this surface, on the contour. And then depending what we're calculating, if we want Hausdorff distance, we take the maximum, and if we want average surface distance, we take the average. And of course, we'll do that for both cases, and then take the maximum of an average or an average of the two values. So you can see that for this example, we have 24 millimeters Hausdorff distance, which is quite large. But it does make sense because you see, for example, these contours here are very far from the ground truth surface, right? So we can see some high values here, or the ones in the background as well. So if we take the maximum, we get the maximum error that we get that is there. So it turns out to be 24 millimeters, which is huge. That tells us that this segmentation is not particularly robust. Average surface distance is 1.12 millimeters, which is a bit better, but given that fetal brain is very small, this is still quite a large number. So it does show that this segmentation was not particularly successful. And the final thing I want to discuss is why don't we use standard measures that we use, for example, for machine learning, so accuracy, precision, or recall. So let's have a look at these measures for image segmentation. Let's start with accuracy. So accuracy is a proportion of correctly segmented voxels, and it is calculated as true positives plus true negatives. So true positives, you know, are correctly segmented voxels, and true negatives are correctly segmented background voxels, we can say. So the voxels that were correctly not segmented, we can say. And then this is just all the voxels in the image. So the problem with that is that we are not really so interested in accuracy of segmented the background, because size of the background actually can vary a lot depending on how we crop the image and so on. So here you can see that there is quite a lot of background in this image compared to the foreground structure, which is cortex. So accuracy becomes quite high, 0.95, but it's driven by these background voxels. And also size of the background may vary depending on how we crop the image, and here we enlarge it. And just by enlarging the background, we could get to 0.99. So you see that this is really not a good measure of segmentation quality. And the reason for that is that the true negatives or a correctly segmented background is not really meaningful for our application. So it's not a good idea to use accuracy for segmentation. So what about precision? So precision is also called positive predictive value. And it's a proportion of correctly segmented voxels in automated segmentation. So here in the denominator, we have true positives, which is correctly segmented voxels of the positive class. And in the denominator, we have number of voxels in automated segmentation. So true positives plus false positives. So that's all the positives, so all the voxels in automated segmentation. So this seems a useful measure actually, because it doesn't take true negatives into account. Then we have recall as well, which is in other words called sensitivity. And this is proportion of correctly segmented voxels in ground truth segmentation. So you can see again, we have correctly segmented positive voxels in the numerator and denominator. We have true positives plus false negatives. So these are all the voxels that should have been positive. So that's our ground truth segmentation. So these two measures are very useful and they are complementary to each other because they will tell us about whether the segmentation was over-segmented or whether some voxels were actually missed. And then we often like to calculate the composite score of precision and recall, which is a harmonic mean of these two measures. And that can be expressed as 2 times precision times recall divided by precision plus recall. And when we do the maths, we will find out that this is actually exactly Dye's coefficient. So true positives, that's the intersection. So, and it was 2 times number of voxels in intersection. And the denominator is actually not union, sorry about that, but instead is number of voxels in automated segmentations plus number of voxels in ground truth. So if you add these two denominators, you get exactly this. So that's why F1 score is really what we're interested in. So to fully evaluate your segmentation, calculate F1 score, recall, and precision. And also accuracy, specificity, and negative predictive value are not suitable because they look at true negatives, which are meaningless. So this is all I wanted to tell you about evaluating the segmentation. And now watch the second part of the lecture, which will be on label propagation.